Okay, we got a homework problem where there is a hose. Here, I'm going to use my colored pins. We got a hose, and we want to get water. So this is right at the ground, off a purple ground. And I want the water to, it's going to follow a parabolic arc. And I want this to end up 2.5 meters away. So I'm not going to call this, okay, so it says, let's see, a fire hose held near the ground shoots water at a speed of 6.5 meters per second out of the nozzle. And it wants to know which angle, actually there's two of them, should the nozzle point in order for the water to land 2.5 meters away. Okay, so before I do this, I'm going to draw something here, and I'm going to say this has an initial velocity, v naught. I'm going to show it just like that. It's going to be a vector, and I'm going to label it. I'm going to choose whatever name I want for it, and then I'm going to call this an angle. So theta is commonly used for angles. And then I'm going to say this is going to be my x and y axis, and it's going to be over here. So this is what I'm calling 0. So it's starting from 0 on both the x and y positions, and it's going to go a distance x. Okay? So I want to use this problem to show sort of a generic way to approach any problem and hopefully not get confused. So you're going to be able to use a pretty stringent kind of math, but the notation, I hope, is going to help you kind of keep track of what to plug in where, which variables to use, what you know and what you don't know. I know as you get going along with these physics problems, it's easy to get lost. You'll absolutely know that this is some kind of trajectory. It's going to involve probably this equation plus 1/2 a and plus this equation. Now I know you are going to go back in your book and you're going to desperately try to find an equation that you can just apply here and skip to the end. And there actually is one. It's buried in an example, and it's given by this. So the range r is equal to v naught squared sine 2 theta over g. Now, this becomes a really simple problem if you know where this equation came from and you know what to apply, like what numbers to plug in. If you do this kind of thing where you look back for an equation and start plugging numbers in, I'm going to tell you that you're going to get about a C or a B grade in this class. As much as I try to help you, if you're just trying to memorize equations, jot down as many equations as you can and just hope that you're choosing the right one and plug in variables, we're going to give you extra credit. So if you memorize this equation and put it, or not extra credit, but partial credit. If you had a test problem where you put this in, you might plug in the wrong numbers, but we'd see, okay, well, this kind of equation applies. We'd give you partial credit. You'll probably pass the class, but you're not going to get a great grade. If you want to get a good grade, like a high B or an A, don't memorize this stuff. Just memorize the simplest equations. So these guys. This is going to give you the position as a function of time for an initial velocity and an initial acceleration. So what I want you to do is write down the beginning equations that you think you'll need. Okay? And now I'm going to want you to write down which of these variables do you know. You could say knowns, or you could call these givens. So you want your x position, your final x position, to be 2.5 meters away. And this is what you want to happen. By definition, you've chosen your axes, which you've drawn, to be 0. So you know that one. I'm just going through systematically and saying, do I know this variable? Do I know this? V naught x, I don't really know. So I'm not going to write that in the list. Time, that's going to be the total time that this droplet of water goes from the hose over to here. I don't know what that one is. So I'm going to say unknown so far. I don't know V naught x. And I don't know time. The acceleration in the x direction is 0. Right? That's the whole thing with projectile motion, is there's no acceleration, or we're ignoring the acceleration due to slowdown of the air resistance. So that's 0. I also know my final value of y is going to be 0. So it's going to land on the ground. My initial value of y is 0. And I don't know VOY. And my acceleration in the y direction is gravity. So AY is equal to negative g, which is equal to negative 9.8 meters per second squared. Okay. Now, the temptation is to start plugging these numbers in right away. Do not do it. Use these variables that you came out with. This is what we're teaching you in class. The physics is all right, but what we're really teaching you is how to read equations and how to use them, how to apply them to real quantities. Okay, so what I can do is plug in the zeros at least. So this one becomes 0, or no. This is going to be 0. Let's see, V naught x, I don't know what. This is going to be 0. So this equation is going to become x is equal to V naught x t. Okay. Here my y naught is 0. I don't know V naught y. I know that this is g. So y is equal to V naught y times time minus 1/2 g t squared. Again, I want to keep this all symbolic, because eventually what you're going to learn is how to read this. Well, this is the position in the y direction as a function of time, and this is my initial velocity in the y direction. If you start plugging in numbers right away, eventually you're going to copy them down wrong. We see it all the time. You make a mistake, and it's just a lot of writing, and don't do that to yourself. Just use these variables. Okay, so the key here is to count the number of equations I have. So this equation came from this one. It's basically the same thing. This equation came from this one. This is equation 1, this is equation 2. I've got 2 equations, and I've got three unknowns. So I'm going to need some more physics. I need one more equation. I need the number of separate equations to equal the number of unknowns. So if that, then can solve. I can solve my equation. So I need one more thing. Well, what is it? Well, pay attention over here. If we know what the magnitude of this initial velocity is, we just don't know what the angle is. And if we've got some arbitrary angle theta, and this is V naught, then I know that the x component of V naught x, or V naught, is V naught x. And the y component over here is V naught y. And we can just figure out trigonometry, right? So let's see. The cosine of theta is the adjacent over the hypotenuse, so it's going to be V naught x over just the magnitude of V naught, so I'm going to write it like that. And the sine of theta is equal to the opposite over the hypotenuse. So there we go. Okay, well now I've got some more equations here, so I can plug this in into equation 1. So now I shift my v naught around. I'm going to get v naught cosine theta, and this equation becomes v naught y is equal to v naught sine theta. And now I can kind of plug these back into here. So what have I done so far? I've derived two equations that I think I'm going to need. I've identified which of those variables in there I know, which ones I don't know. I've got more unknowns than knowns, so I needed more equations. And I realized that, well, v naught at x and v naught y are related somehow. They can't just be anything. They're going to be adding up to a certain magnitude, which is a given. So I know the magnitude is equal to, I think, 6.5 meters per second squared, if I'm right. Chapter 4, where am I? Yep. 6.5 meters per second. So now I'm going to plug this into here, and I get, still, I'm not going to plug numbers in yet. So now just plug this in for v naught x. And I'm going to do the same thing for v naught y. So over here, I've got v naught now sine theta times time minus 1/2 gt squared. Okay, now look at this. I've got two equations. I know what I want this to be. This is going to be 2.5. I know what this is. I don't know theta and I don't know time. But I've got another equation here. I know what y is. That's going to be 0. It's going to end up back on the ground. I know v naught. I know that that's 6.5 meters a second. Theta, I'm checking my list over here. I'm saying theta, I don't know theta. That's an unknown. So I've got two new equations. Unknowns are time and theta. So I can solve in principle. Okay, so now what do we do? Well, here's a strategy. You want theta. You don't really care about the time. You don't really care right now. The question's not asking you how long is the water in the air. It's asking you what angle do you want. So what you do is you choose the shortest, simplest of your equation. So that would be this one. Then solve for what you do not want. So don't care about. So I'll tell you why in a bit. As an example, we don't really care about time, so I'm going to take my simplest, shortest equation, and I'm going to solve for time. So I'm going to divide both sides by v naught cosine theta. So I'm going to get x over v naught cosine theta. I'll get v naught cosine theta over v naught cosine theta. That's 1. So I've just solved for time. And now what I'm going to do is I'm going to plug this back into the next equation. And I'm going to get an equation that doesn't have time in it, which is great because I don't want an equation with time and I don't care about time. I want theta. Okay, I'm going to go ahead and plug in the fact that y equals 0 at this next stage. So 0. So this part became this, and then I had this equation plus this equation kind of going into this next bit. So 0 is equal to v naught sine theta times time. That's going to be x over v naught cosine theta minus 1/2 g times time squared. So I'm going to have x over v naught cosine theta squared. So it's going to be x squared v naught squared cosine theta squared. Okay, let's see. I'm going to cancel these out. I got v naught sine theta divided by v naught cosine theta. So those divide out to 1. I've got 1 cosine theta on the bottom here, and I've got cosine squared theta here. So I'm going to multiply through by cosine squared theta. Cosine squared theta is going to be times 0 is 0. It's going to be 0. We're going to get a sine theta, cosine squared theta, my x, and my cosine theta down here. But this one's going to cancel out with one of those. And minus 1/2 g x squared over v naught squared. Because when I multiplied through by my cosine squared theta, these ones canceled out. Okay, so now I'm starting to get a term that looks like it only cares about theta. So I'm going to get sine theta, cosine theta, times x. I'm going to add 1/2 g x squared over v naught squared to both sides. So this part will go away. And it goes around to the other side. 1/2 g x squared v naught squared. And then I'm going to divide by x. So I'm going to get sine theta cosine theta is equal to g times x, that's the range that it goes. So the x squared divided by x is just going to give me x over 2v naught. Okay. And I want to know, I know g, that's 9.8, x is 2.5, v naught is 6.5, and 2 is 2. And I got my unknown on the other side, so how do I solve this? Well, here's where you use a trig identity. And I can never remember these either, but fortunately we got a great book. One of the many reasons this is a requirement for the class. You might even want to keep this around because guaranteed eventually you are going to use physics in your career, in your household. And look at this. I've got a sine theta, cosine theta. I've got a factor of 2 in there. And I've got something that's a little bit simpler. Okay. So I've got, if 2 were on the other side, I'm going to start a new piece of paper. I've got, going to multiply both sides by 2, so I have 2 sine theta cosine theta, and that trig identity tells me that this is equal to sine of 2 theta. Now even this, eventually with practice, you'll be able to derive this, and you'll even be able to recognize when to do this. But for now, all I know is I had a bunch of knowns on one side and one unknown on the other side, so I could, in principle, solve for this. And this is going to be equal to, I multiply both sides by 2, so I get gx over v naught. I think I lost a v naught squared. Yeah. Okay. And then look at this. This is starting to look like my original equation that I could have found if I was really paying attention to the textbook and I really understood everything as I went through. I'd start to see, wait, this looks kind of familiar. My x is my range. And if I solved for x here, I would get this equation. But I don't want to solve for range. I know what the range is. I want to solve for theta. And so theta, or 2 theta, would be the inverse sine of gx over v naught squared. And so theta would equal 1/2 inverse sine or arc sine of gx over v naught squared. Okay. Now, if you plug in, now is the time where you're going to plug in these known values. Only now. What you might do already is you know, anytime you take a sine or an inverse sine of something, this can't have any units. So we could go ahead and check our work to see if we are spot on. So 9.8 meters per second squared. X is 2.5 meters. And then I've got V naught squared, that's 6.5 meters per second squared. I'm taking the inverse sine of this. Okay, well here I'm going to get second squared on the bottom, and I've got 1 over second squared here, so those are going to cancel out. I'm going to have meters times meters, that's meters squared, and I'm going to have meters squared here, so those will cancel out. So sure enough, I don't have units here, that's what I want. So theta is equal to 1/2 inverse sine of whatever 9.8 times 2.5 divided by 6.5 is. Now the problem is asking for two angles, and it turns out that I think something like 17 degrees and 74 degrees or something like that will solve this problem. Okay, so I just want to summarize the technique that you can use for a wide range of physics problems that you're going to get lost and stuff in. Is I write down some basic equations that I know how to use. So these are two. I draw a diagram, and I label the diagram with variables that I'm going to remember. So I recommend things like X and Y and R and stuff like that for positions. I'm going to draw my coordinate axes, and then I'm going to make a list of what the problem gives me in terms of my variables. So V naught is equal to this, X is equal to this, X naught is equal to this. I'm going through systematically and saying which of these do I know and which of these do I not know. And then I'm going to count my unknowns and my number of equations, and that's going to tell me whether I can stop and start doing algebra or whether I need to kind of figure some more physics out. Sure enough, I had 3 unknowns and just two equations, so I needed one more. And then I realized that V naught X and V naught Y were related, and I had one more known that I wasn't using, and I could relate them by this trigonometry. So I was able to solve V naught X in terms of a known and this angle, which I want to know in the end, and simplify this, get a new equation. So I got 2 new equations with 2 unknowns, time and theta. And then I told you, okay, well, how do we solve this? Well, do some algebra, try to solve for the equation or the variable that you don't know and don't care about, which is time in this case. Use the simpler of the equations. And then now that you know what this variable is in terms of this stuff, you plug it into the more complicated equation. And now you've got one equation with just one unknown, so in principle you can solve for theta. This one was tricky, we had to use this trig identity. But welcome to university. You're going to have to figure out these tricks. You see something like this, you're going to have to look it up somewhere. Fortunately, your book has a lot of these tricks, maybe even all of them.